Again, welcome to DSRT 734 class. This lectures cover the Bayes Theorem. So suppose that 85% of all passengers in an airport fly on a major airline, while the remaining 50% fly on a small airline. Of those passengers travel on a major airline, suppose we know that 65% travel for business. Then of those passengers travel on a small airline, we know 25% travel for business. Now, our question is that what is the probability that the business passenger travel on a major airline? Now, we should notice that even though we are only talking about business passengers, there are also non-business passengers. So let's first define the events associated with this problem. We have a major airline as M, small airline as S, then the business passenger as B. So the following probabilities are given to us in the problem. The probability of M, which is probability of passengers flying on the major airline, is 85 or 0.85 or 85%. Then the probability of passengers flying on the small airline is 15% or 0.15. We are also given the probability of B given M, which is 0.65. That's probability of business passenger given the major airline. And also we have the probability of a business class passenger given the small airline is 0.25. Now, to determine the probability that the selected passenger or the business passenger travel on a major airline, then we are looking for probability of M given B. Using the four probabilities above and also the Bayes theorem, we can proceed as following. So we know the probability of M given B is equal to probability of M and B divided by probability of B. So this is again our conditional probability formula. Probability of M given B will be the probability of M and B divided by probability of B. Now we know the probability of B, we have both major airline and small airline for the passengers. So probability of B is the same as saying probability of B and M plus probability of B and S. And here we say by definition of a conditional probability, the denominator says that all business passengers travel either on a major airline or a small airline. So those are the only two alternatives and they are mutually exclusive. One passenger cannot go both major and small airline at the same time. So that means probability of B is the same as saying probability of B and M plus the probability of B and S. Again, M represent the major airline, S represent the small airline. And that will lead us to the concept of Bayes. So we know the conditional probability. We say probability of B and M is the same as probability of M times probability of B given M plus probability of S times probability of B given S. Because probability of B and S is the same as probability of S times probability of B given S, or probability of B times probability of S given B. So from here, we can plug our values, which almost all of them are given to us. So we have 0.85 times 0.65 divided by 0.85 times 0.65 plus 0.15 plus times 0.25. So this will give us roughly 94% of 0.936. Therefore, we know that if a passenger was traveling for business, there is 94% chance that he or she will be traveling on a major airline. So the concept we use here is Bayes Theorem. And here we said that notice how the conditional probability of 94% is not intuitive. And also it's called the posterior probability. The prior probability of a passenger travel on a major airline, it was 85%. Now it has been increased to 94%, giving the formation that the passenger was travel for business purposes. So this will lead us to the Bayes Theorem. And here, let's say A be an event, and also B1, B2, Bn, Bn mutually exclusive and collectively exhaustive event. Then Bayes' theorem will be probability of Bi given A is equal to probability of Bi and A divided by probability of A. Now we know probability of A will give us the possible of By, B2 up to Bn. So probability of A is the same as saying probability of A and B1 plus A and B2 plus A and Bn. And this will lead us to, again, we know the probability of Bi and A is the same as saying probability of Bi times probability of A given Bi. And the same thing for the denominator also. So we get probability of B1 times probability of A given B1 plus probability of B2 times probability of A given B2 up to probability of Bn times probability of A given Bn. Because we know probability of B1 times probability of A given B1 is equal to probability of B1 and A. So that's the whole concept of Bayes' theorem. Now let's see one example here. Let D be the event that a person has a rare disease. So suppose that the rare disease has an incidence rate of 1% in the population, which means probability of D is 0.01, which is probability of the complement of D will be 0.99. So D bar is the event that a person does not have the rare disease. So if D is 0.01, then complement of D will be 0.99. Now, suppose a machine is used to diagnose the disease. Let C be the event that the disease is confirmed as the diagnosis. Now, suppose that the probability of the machine falsely confirming the disease when one doesn't have it is probability of C given complement of D is 0.15. We call this the false positive. So while the probability of C given D is 0.95, which says that the machine correctly confirmed the disease with an accuracy of 95%. Now, suppose that the machine confirms that the person has the disease. What is the probability that the person actually has the disease? In other words, we are looking for probability of D given C. So here are the probabilities given to us in the problem. First, we know the probability of D is given to be 0.01. So probability of D complement will be 0.99. Also, we know probability of C given D is 0.95, is given to us. And also probability of C given D complement is given to us to be 0.15. Now, to find the probability that a person with a positive diagnostic result actually has the disease, we proceed as following. That is probability of D given C is equal to probability of D and C divided by probability of C. Now we come up with the idea of Bayes' theorem. Probability of C, we have only two options. Either we have the disease or we don't have the disease. So probability of C is the same as probability of C and D plus probability of C and D complement. Then we know probability of D and C will be probability of D times probability of C given D, divided by probability of C and D will be probability of D times probability of C given D, plus probability of D complement times probability of B, the probability of C given D complement. So again, this is the Bayes theorem to solve the problem. So we can see that we have most of the values and we plug in all the values given to us. So the correct answer will be 0.06, which means a 6% probability of D giving C, which is the question said probability of D giving C. So that will be 6%. So this is somewhat of assuring result in that you have only 6% chance of having this disease, even though the machine yielded a positive diagnostic. We still have only 6% chance of having the disease. So that will be the conclusion of these lectures. Again, this is a very short lectures, and our main goal is to cover the Bayes theorem. And this is again the definition. In Bayes theorem, if you have A be an event, then we have a couple of B1, B2 up to Bn mutually exclusive, but they are collectively exhaustive events. Exhaustive event means, for example, we saw the probability concept about having the disease or you don't have the disease. There's no any third option no more. Either you have the disease or you don't have the disease. So it will be B1, B2. Or another example, the first example we did is the same concept again. And the airline have only two options. Either you fly as a business class or you fly as non-business class. So this means the event will be mutually exclusive. We cannot fly at the same time with business class and non-business class. We have to take only one. So which means it's mutually exclusive. And collective exhaustive means we have only two options, not more than two. So if these two conditions, which is mutually exclusive and collectively exhaustive events, then we can use the Bayes theorem to solve the problem. So again, wish everybody the best and thank you for your time.